Examples. We can illustrate this approach by using several examples where f colon open bracket 0 comma 1 close bracket yields all real numbers. Our first maximization problem is max with x underneath, negative 1 half, open parentheses x minus 1 half, close parentheses squared. The first order condition is the derivative of f of x with respect to x equals 1 half minus x equals 0. So x star equals 1 half. As panel A of figure capital A dot 7 shows, the second order condition is the second derivative of f of x star with respect to x equals negative 1 less than 0. So 1 half is a maximum. Once one can demonstrate that this function f is continuously differentiable and concave throughout the domain. So f of 1 half equals 0. Point A is the global maximum of this function. Now consider the maximization problem. Max x 1 half, open parentheses, x minus 1 half, close parentheses, squared. The first order condition is the derivative of f of x with respect to x equals x minus 1 half equals 0. So this problem has the same critical value, x equals 1 half, as in the previous example. Because f is continuously differentiable, we know that it has a maximum and a minimum on open bracket 0 comma 1 close bracket. The second order condition is the second derivative of f of 1 half with respect to x equals 1 is greater than 0. So x star equals 1 half is a minimum, as panel B of figure capital A dot 7 shows. There are two global maxima which are not interior at 0 and x equals 1. The maximization problem, max x 1/3 open parentheses x minus 1 half close parentheses to the power 3 has a first order condition. The derivative of f of x with respect to x equals open parentheses x minus 1 half close parentheses to the second power equals 0. So the critical value is again at x equals 1 half, because f is continuously differentiable. We know it has a maximum on open bracket 0 comma 1 close bracket. But as in the previous example, the maximum is not interior. Instead, it occurs at x equals 1. This function is neither concave nor convex at x equals 1 half. So x star equals 1 half is neither a minimum nor a maximum of f. As panel C of figure capital A dot 7 illustrates, it is called a saddle point. We have a saddle point when the second order condition is 0, as in this case, the second derivative of f of 1 half with respect to x equals 2 times open parentheses x minus 1 half close parentheses equals 2 times open parentheses 1 half minus 1 half close parentheses equals 0. The sign of the second derivative changes from one side to the other of the saddle point. Finally, the maximization problem, max x of the natural log of x plus 1 yields the first order condition 1 over open parentheses x plus 1 close parentheses equals 0. Here, f is continuously differentiable and strictly concave. So we know that a unique global maximum exists. However, there is no value of x in the open bracket 0 comma 1 close bracket interval that solves the first order condition. Consequently, we know that the unique global maximum is not interior. In this case, it occurs at the endpoint where x equals 1, as panel D of figure capital A.7 illustrates. More generally, we may want to find the maximum of a function of several variables, and hence several choice variables appear under the max operator. To use calculus to solve such a maximization problem, we compute the partial derivatives of the objective function with respect to each of the voice choice variables and then set these equal to 0. These equations in which the first order partial derivatives are set equal to 0 are called the first order conditions. For example, let g column open bracket 0 comma 1 close bracket times open bracket 0 comma 1 close bracket yield all real numbers, and assume that g is continuously differentiable and strictly concave. Then we know, as we did for f, that g has a unique global maximum. Accordingly, we can write the problem as max x sub 1 and x sub 2 of g of x sub 1 and x sub 2, which yields the pair of first order conditions, a partial derivative of g of x1 and x2 with respect to x1 equals 0 equation capital A dot 3, and the partial derivative of x sub 1 and x sub 2 with respect to x sub 2 equals 0 equation capital A dot 4. The solution to equations capital A dot 3 and capital A dot 4 determines where the global maximum of G is located if a solution exists. If a solution to these equations does not exist, then the maximum must lie on the boundary of the choice set open bracket 0 comma 1 close bracket times open bracket 0 comma 1 close bracket. So either x1 or x2 or both must be equal to either 0 or 1 at the maximum.